Okay, so we have rho, theta, and phi. Rho, theta, and phi. Those are your spherical variables. Rho, theta, phi. Okay, rho is used for like density, in your physical science class or whatever. So, okay, so let's take a look at, in blue, let's use red actually for our cylindrical coordinates. So cylindrical coordinates, basically you take your x, y plane and you measure the distance to the point below point P. That's your r. So this little distance is r. And this is theta. These are the same r and theta you guys used in the polar world. Exact same r and theta. And then just going straight up from that point up to point P, that's the distance z. And those are called your cylindrical coordinates. R, theta, z, in that order. Okay, and then the spherical coordinates, remember, is more of a straight shot thing. You measure the blue from the origin to the point, but then you need two angles to define it. We use theta again, and we use phi. So I was saying yesterday, some people like to write theta like this, but oftentimes you'll see it written in cursive. And same thing with phi. Phi, you might see it written like this, but a lot of my worksheets look more like that. So it's kind of the script version, I guess. Okay, so rho is the distance, and the two angles are theta and phi. Okay, so let's try creating these formulas. Like, how do you go from red to blue or from blue to red is the question here. So, I don't know, point P. Maybe that was a bad choice. What do you guys want to call the point?
Q.
How about Q? Great. But that looks like a phi.
That's even better.
How about we use H for Hunter since he's complaining? He's the one complaining. Just kidding. Okay, so how do you find rho using red only? So how do you find rho using red only? Well, there's a right triangle here. You can see it. Right, see the right triangle? So r squared plus z squared should be rho squared. So you could use rho equals square root of r squared plus z squared. Or sorry, rho is square root of r squared plus z squared. And then theta, well, it's the same theta you used in the cylindrical world, so you could just borrow that. Phi, or some people call it phi. You can call it phi, phi, faux, fum. Doesn't matter to me. I said that same joke yesterday. I got a new one for you, though. Why do mathematicians, prefer cylindrical coordinate system cell phone providers versus spherical coordinate systems cell phone providers? It's because of all the hidden fees.
Oh, yes. That is the best one yet.
There is a fee.
Was that the one John said?
John made that. That's a great joke. That's a great joke. In the spherical world, there is a hidden fee right here. A hidden fee. I like it. I shall laugh about it more later, but for now, I'm moving on. Okay, do you guys see that these two angles are actually the same? They're alternate interior angles? Yeah. Basic geometry? Okay. But that's important because that's the one inside our triangle, so we'd rather use the green. Okay, well anyway, you can see that the relationship between red and blue here, one of the relationships you could write, is that phi is inverse cosine of z over rho. But rho is square root of r squared plus z squared, so we probably shouldn't use any spherical coordinates to find spherical coordinates, So you're trying to basically use only r's and z's and thetas on the right. So I just stole the rho from up above. So basically it's inverse cosine of z over rho, where rho is what I wrote on the first line. Okay, if you want to go from spherical to cylindrical, then you're supposed to use the blues to write the reds. See? So how would you write R? So just looking at your triangle there, I'm going to draw it from the side. This distance is r, this distance is z, this distance is rho, this angle is phi. Here's your right angle. So I'm looking at this triangle here from this, just kind of a head-on view. Okay, I'm looking at that triangle. So if you want to isolate r or write down something meaningful that involves r, and you really want only, r's, thetas, and phis, you probably don't need the z there. So isn't it true that sine phi is r over rho? So you could think of it as r equals rho sine phi. Sorry, I don't know why I had an r squared there. It should say r equals rho sine phi. It just comes from the right triangle that we just drew. The theta is the same theta as cylindrical world, so you can steal that. Theta equals theta. And as for z, now we'll put that z back into the picture. That z is basically rho cos phi. Okay, so I hope you watched the video last night, but if not, just know that there's a lot more formulas that you missed out on. So there's formulas for rectangular to cylindrical, cylindrical to rectangular, rectangular to spherical, spherical to rectangular, and probably the spherical to rectangular are the most complicated ones. So you can either copy those from somebody or just watch the video. That way you'll also understand it, hopefully. But we do have three systems for measuring the coordinates of a point in 3 space. Okay, so let's say you wanted to convert 3, 4, 5 from rectangular to spherical, right? So understand that this must be an x, y, and a z. How do I know that? Because it says that this is rectangular. It says that. So if that's x, y, and z, and we're trying to convert, we're going to be trying to get this to give us rho, theta, and phi. I think you should put your calculator in degrees mode.
Is this something we're generally going to be using our calculator for?
Yeah, almost always. In fact, I've tried really hard before to write questions that come out to nice, clean answers. Unit circle angle all the time. It's almost impossible. So just expect to use your calculator, I guess. Bless you. Okay, we're going to be trying to do this, so we need a set of formulas that will do this for us. And the first one we have is that rho is equal to the square root of x squared plus y squared plus z squared. So that would just be basically the square root of 9 plus 16 plus 25, which is square root of 50, or you could say 5 root 2. Okay, so that one's done. Now let's go ahead and get theta. So theta is just inverse tan, basically, of y over x. Inverse tan of y over x. So basically 4 over 3. And I won't be adding 180 because 3 is a positive number, so don't add 180. But your calculator will give you this angle. I think it's 53.130, if I remember correctly. And then lastly, phi. So phi is rectangular to spherical, just cos inverse of 5 over rho. And we just found rho back in the first question there, so 5 root 2. So I'm stealing the answer for rho and placing it right here. So you end up with basically 1 over root 2, which is root 2 over 2, and all this inverse cosine comes out to 45 degrees. So sometimes, sometimes you don't need a calculator, but most of these angles you would probably. So here's your answer, and you should write it in this order, please. 9 out of 10 textbooks agree that it goes in the order rho, theta, phi. Okay, so we'll write 5 root 2, 53.130, comma, 45 degrees. Rho, theta, and phi. All right, let's try the next one. This time we're converting from cylindrical to spherical. So evidently they're giving us, I guess this is just an r, and this must be theta, see? And that must be a z, because they said cylindrical. Well, one thing's for sure, our theta is pi over 4, you could steal that. So I'm going to start writing my answer right now because it feels good to have part of it done. Pi over 4. Nice. I just stole that. It's the same theta used in both worlds. Okay, but we do have to find rho. So rho is the square root of r squared plus z squared. In other words, 6 plus 2. So basically 2 root 2 goes in the first blank. And phi is phi is inverse cosine z over square root of r squared plus z squared. This is r squared plus z squared. But that basically is, this is what happened to us last time. We stole our radial distance from our work earlier. So this is just going to go here.
45 degrees again.
Yeah, it is. So this is cos inverse root 2. No, it's 60 degrees this time over 2 root 2. This time it's the root 2's that cancel. See? So this time we get 60 degrees, but now I feel obligated to put it in, radian form because I'm going to have that pi over 4 there. So why don't we write pi over 3? Pi over 3. So this brings up a question. Should we go with degrees or should we go with radians? I personally think you should do degrees because especially if a student writes this in like decimal notation, like they would write this as, 2.8-ish, and then that's, like 0.7 something, and then they write this as, 1.07. You can't tell these are angles. They look all like distances, So if you plan on using radians, keep the pi's in there, or write a little r above each of these so I know these are angles. If you go with degrees, that's a non-issue because you would just write 2 root 2, 45 degrees, 60 degrees. When I see the degrees, I'll know those are angles. Okay? So please don't just give me 3 decimals and expect me to figure out which ones are angles. The next one should say cylindrical here. It was a typo on the notes. We've already done a rectangular to spherical, so I was hoping we could try some variety. On part C, can you guys fix that to make it look like my yellow there? If you printed it at home, then it already looks like that. Okay, convert from rectangular to cylindrical. So we basically are being given x, y, and z. We want r, theta, z. So we can steal the z anyway. So it's just going to be negative root 2. Feels good to have that part done. Let's go to look at r and theta and what those would be. So fortunately, r is the same definition as back in the polar world. It's the exact same thing. I'm really glad they didn't switch that up. So it's negative 1 squared plus 1 squared. It's just root 2. And then theta is just inverse tan y over x plus 180 in this problem. Why? What's negative? X is negative. Very, very important. If you type inverse tan of 1 over negative 1 in your calculator is going to say negative 45 degrees. Okay? You need to remember to add 180, otherwise it's not going to make any sense. How can a point with a negative x coordinate and a positive y coordinate end up in quadrant 4? That's impossible. So you just have to use your common sense. Negative 1, 1 is a quadrant 2 angle. Right? A quadrant 2 point. So it should have a quadrant 2 angle. 135, not negative 45. If you think you might mess that up, memorize it this very, very simple way. When you're doing an inverse tan, if your denominator is negative, always, always, always have an angle. It's that simple. Okay? All right? Okay, so that's what we did yesterday was I developed the formulas for you. I don't know, someday I might have my students actually do that by hand, but it's kind of hard. And then we got the examples there. And I guess I never did spherical to cylindrical for you. But, you have the formulas, and this is probably enough examples for you to get the ball rolling. And this will take you a while. When you're doing the worksheet, be very careful. Be very careful with your calculations. Yeah?
135.
I do that. 135, not 145. I was just making sure you're awake. And you are. Okay. let's go down and talk about these surfaces. What is this talking about? So it's really important that you do something like this before you jump into any complicated Calc 3. You really need to learn to read an equation. You have to notice what variables are present, what variables are absent, and be able to visualize that object in 3D. Okay? Okay. So the first question says, identify the surface r equals 5. Okay. Now they probably didn't need to tell me that it was a cylindrical coordinate equation. R equals 5 just sounds cylindrical. R only shows up in the cylindrical world anyway, right? Okay, so, but they might need to tell me on another problem. So they did tell me. Anyway, r equals 5, what would that look like? Let's see. R equals 5. R is the distance to the z-axis. So let's start down here on the xy plane. You might want to draw this. Let's just stay on the xy plane for now. So if this is on a desk, we'll just stay on the desk for now. What would r equals 5 look like in 2 dimensions? You've done it before. You've graphed r equals 5 before. Polar equation, what is it? R equals 5. Just when you graphed r equals 5 in the past, it's a circle, right? In fact, a circle of radius 5. Centered at the origin, right? So this is r equals 5. Notice that this is technically a 3D lesson. So you'll notice that there are some things missing, like theta is not in the equation. I thought cylindrical variables had theta and z, and r. Well, the absence of the theta tells us what? It's any theta we want. That explains why we didn't just draw one point where r was 5. We drew all the different thetas where r was 5. See? Okay. Also, z is missing from my equation, which implies that z can be anything we wish. So if you were here yesterday, I said that the absence of a variable actually screams a truth at us. The z is shouting, use me, even though I'm not in the equation, because I am the most flexible. Theta and z are not determined. So you actually have to stop thinking that, r equals 5 is a circle. You have to start thinking, this is a cylinder. Any circle with radius 5, no matter what its z coordinate is. And the absence of the z tells us that z can be anything. So this goes straight up or straight down, forming this cylindrical look. All right? Now before you say, well, this is all very interesting, but not very appropriate or applicable, please understand that there's a lot of things in this world that are naturally cylindrical, right? For example, if you take, I'm getting a little off topic here, but I think it's important. If you set up a magnetic field like this, some of you might want to pay attention. Some of you are not. If you set up a magnetic field, a uniform magnetic field, you'll never get the field lines perfectly straight. But let's say you do a pretty good job getting these field lines. Don't need that. You get the field lines pretty straight here, almost straight lines. You'll learn later in E&M that that's impossible. But you send an electron flying in. Okay? Here comes the electron. Mr. E minus. He flies in. When he hits that, it's kind of like a fox running into the forest, But when it goes straight into that field, it's going to find a field line to wrap itself around forever. And as it wraps around, it will emit radiation. Because when you cause a charge to change its direction of travel, it emits radiation. It actually shoots off photons. Photons come from that electron and fly off in a direction normal to the circle. So what's going to happen is this thing's going to go in here and it's going to start wrapping around. And it's going to pick a constant radius and it's just going to go around and around and around. And you can measure its radius, you can predict its radius. The faster it goes in, the bigger the orbit it will have when it swings around a field line. The slower it goes in, the tighter the orbit. Okay, this happens to particles from the sun. They hit our radiation, our magnetic belt of the Earth, and they come streaming in towards the North Pole. And as the field lines come together, please listen. When the field lines come together, okay, the density of the field lines causes a repulsion effect, and that charge starts to spin faster and faster, and then it turns around and goes back the other way. And when it does, it emits the northern lights. That's where it's from. Okay? So when the field lines are present, an electron will choose to travel around it always. Well, what's happening when something goes around and around is its theta is changing, but its r isn't. You would never want to measure the position of this moving object using x, y, and z. It's a horrible, horrible choice. You would rather use r, theta, and z. Do you know which z it's at? You know its radius of travel? Theta is changing, but r isn't. So much better than x, y, and z. If it comes in with a slight vertical velocity on its way in, so here comes a different electron. It comes in sort of at an upwards angle. When it hits this field line, it's still going to take on a circular path, but it's got a vertical component of velocity. So it's going to travel along this more spiral look, or helical motion, H-E-L-I-C-A-L, the motion of a helix, right? You know, DNA, the twisted ladder thing, right? So it takes on a helical motion, and while its z might be changing up the page, the r isn't. The theta is changing, the z is changing, but the r isn't. So it's just better to use cylindrical than it would be to use x, y, and z, which are always changing at all times. So it's just a natural phenomenon that would lend itself better to cylindrical coordinates than Cartesian. Can you imagine a situation in our world, or at least our solar system, where you'd probably rather use spherical coordinates than anything else? Why would you ever want to use spherical coordinates?
Location of the planets.
Yeah, on a planetary orbit, right? You've probably got a constant rho, that means distance from the Earth to the moon or whatever, or sun to the Earth, relatively constant r, or rho. And then you've got maybe one angle changing, maybe two angles changing at all times. But at least something's constant. Nobody ever uses x, y, and z in outer space. Besides, which way is up and down, right? It's more about ins and outs and approaching and leaving and angles and planes and that sort of thing. So I think it's important that I mention this because I don't want you to think that this is totally arbitrary and useless knowledge, okay? Okay, what about this second equation? So we decided that this was a cylinder with radius 5, so we can title that. Cylinder r squared plus z squared equals 100. So that's a little hard to visualize. You know, like what I just did a minute ago, I sort of sketched it and figured out that was a cylinder. I don't think I could do that on this one. Maybe I could. But look back at your equations. Do you see r squared plus z squared anywhere in your work?
Rho squared.
Yeah, this is rho squared, right? So this is just basically saying that rho squared is 100. In other words, rho is 10 is all it means. This is sort of the spherical version, the spherical way to write r squared plus z squared equals 100. So in this problem, I wasn't able to sketch it and understand it, but I was able to convert it, and I think I understand it. Remember, rho means the distance from the origin to the point. If the distance from the origin to the point is 10, and nothing else is given, what kind of shape is that? Remember, rho is literally this, guys. Here's your coordinates. Rho is this distance right here to point H. This is rho. Imagine if all I told you was rho was 10. Would you know exactly where point H is? No way. It could be anywhere, right? 10 spaces from the origin. In any direction. It's a ball. Yeah, it's a sphere. So this is a sphere of radius 10. See? So now when I didn't start by sketching, I started by rewriting it. That's a very important skill. Okay, here's this next one. Z equals R. Or maybe you'd like to look at it as R equals Z. Now you've already discussed what R equals 5 was. What was R equals 5 back in part A? It's a cylinder, right. Now let's notice that there's two variables. That means if you're really stuck, you could just make up numbers. So let's say Z was 0. By the way, where is Z equals 0 on these 3D plots?
2D.
If Z is 0, we're talking about
XY plane.
the xy plane, right? Okay, so if Z is 0, we're talking about right here. Z equals 0. The radius is 0. Okay, that's not very interesting. I guess that's just like a little point. Okay, but if z is 1, if you go up a space, oops, I didn't mean to erase. If you go up one space, it would now reads r equals 1. See, I've made z 1. So you go up a space, and now radius is 1. What does that look like? A little bit bigger circle. Now I go up to z equals 2. Now it reads r equals 2. What's that? A little bit bigger circle. Radius 2. See? If I go up to z equals 3, or 4, or 5, as I progress upwards, I get bigger and bigger circles. What is this thing?
Tornado.
Yeah, but it's straight on the edge, right? It has a linear growth. As,
Half of a cone.
what's that?
Half of a cone.
Yeah.
Oh, no, could it be negative? They can't have negative radius.
According to our definition in the notes,
It's a cone.
the r is positive, which implies z would be positive here. But if you want to discuss negative z's on this, you could, I guess. It's going to give you another upside down cone, or technically the other half of the double napped cone. But you see that this is more of a cone-like shape. Why are the edges so straight?
Because
Why is
it's
the edge so
linear growth.
straight? What?
Linear growth.
It's a linear growth. As you double your z, you double your r, see? So these edges look straight to us. Maybe you never noticed that before, but a cone is, by definition, actually just a line rotated around. I think I showed you this yesterday, right? So if you take a line and you just spin it around, sort of let it precess or wobble, that forms a conical look. And the edge, of course, is straight, because the wood is straight on that. So there's a cone, and that's what we would title this, a cone.
A cone? It's both sides, but everyone just says a cone is half. If you would watch the video, you would know.
Yeah, technically, were you here yesterday, Sydney? Okay, yesterday I did say that a cone technically has two parts. A cone technically has a top and a bottom. So this forms the upper half of a cone, is what it's called. Yeah. The lower half, you'd have to extend your r's to allow negatives. Okay, identify the surface for each of these spherical coordinates. Well, the first one's going to be easy because we already discussed it. What's rho equals 5 mean? This is a sphere, right? What about the sphere is 5? It's radius. Yeah. Okay, this next one's a little tricky. Somebody just left. Okay. Well, I'm recording, so hopefully they'll get this. This is a little bit trickier. Theta is, or phi is 60 degrees. You can think in degrees if you like. Phi is 60 degrees. Some people see this right away.
This is the cone as well, right?
It's the same basic idea as the drawing up above there. What's going on is phi is the measure, the angular measure between here and here. That's what phi means, right? So without any specific mention of a direction in which to draw, all we understand this to mean is this. Watch my ruler here. Take this straight z-axis, right, and drop 60 degrees. But it doesn't say which way, right? So I could drop this forward like this, or to the side, 60 degrees, see? Or I could drop it to this side, 60 degrees, or maybe, okay? Right? In other words, it's just any direction, watch close, any direction, 60 degrees. See? Drop 60 degrees in an unpreferred direction. That's a cone, isn't it? So that's also a cone. And it's wrapped around. How do you know that all these thetas are okay? Well, theta's not mentioned in the equation. How do you know that all of these different I'm sorry, actually this is the only independent variable. The only absent variable is, no, theta's missing, rho is missing. Oh yes, that means this cone is infinitely long. Yeah, so this cone is infinitely long. In other words, you can go any distance out along the blue cone from the point 0, 0, 0. So h, could be here, here, lots of different row possibilities. Okay, cool. So that's a cone as well, upper half of a cone. The next one is totally different. This one says theta equals 2 pi over 3. Theta equals 2 pi over 3. Theta has a very different definition. Theta is this distance here, this angle. So this is like theta equals 120, So if this is 0 degrees right here, and this is, the x-axis, then this would be theta equals 90 degrees. And then back here on the other side of our x-axis, this would be theta equals 180. So I guess theta equals 120 would be kind of right in here somewhere. 120 degrees. But there's no mention at all of a radial distance. There's no r in this, no rho, right? And no phi. So if theta is 120, and this is a spherical equation, you could pick any phi you want. So imagine extending this up, approaching the z-axis, because we don't know the angle from it to the z-axis. What's this thing? It's a plane. It's half of a plane, actually. It's a half plane. Yeah, it's a tough one. It's a tough one to see. I'll just start over and draw it again. Maybe this time you'll catch my sketching. So here's the x-axis, here's the y-axis, here's the z-axis. So we know that this is theta equals 0. This is theta equals 90. And this back here is theta equals 180. You agree? 270 is over here. You with me so far? Okay. I am specifically trying to graph theta equals 120, which would be right in here somewhere. But I wasn't told how far out to put my point H. So it could be any of these points here. Any of these black dots could be H. I was also not told which phi to use. Phi, remember, is that drop-down angle from the z-axis. So right now, all of these are phi equals 90. Are you with me still? Every one of these points is a phi equals 90 point because they're all 90 degrees as measured to the z-axis. You see that? But they never said that phi was 90. That's just kind of my first sketch. So now I need to decrease that angle. So I'm going to sweep this up towards the z-axis, allowing for, my ray to be drawn like this, you see. And all the points on here. So I just made my z, 80 degrees. My phi, now it's only 80 degrees to the z-axis, you see. And I can shrink it to, 70 degrees. And these are all my points. Or maybe 60 degrees, or, 10 degrees, or 1 degree, whatever. All of these rays count. All of the points on these rays count. In other words, we kind of created this, like a fan look. Like on those Chinese fans. Someone gave me one for tutoring their kid. I got this neat Chinese fan. You fan it out and you cool yourself up. You know what I'm talking about? Yeah, it's kind of like that, but this goes on forever, so it doesn't have any roundness to it. It's no edges at all. It's just a plane. It's a sheet. Should we draw more to this? Yes, we should allow obtuse phis. Yeah, we should allow 91 degrees and 92 degrees. All the way down to phi equals 180. But if I stretch my Chinese fan like that, I'll probably break it. But it's, yeah, you're right. But why am I calling it a half plane? Planes have no boundaries, right? This goes on forever, like outwards this way. And forever upwards,
Do you have a negative, or in...
Well, if r is positive, we're not allowed to go over to this side, because the angle was specifically the direction of 120, you see, not, 240. So I'm just drawing a half plane. computers do a great job of drawing this stuff. And if you go online, there's a guy named, well, I put his name at the top of my lesson. He just goes by Paul, but he's a professor, and he has a website called Paul's Notes, and it's excellent. I mean, every example's so good, and I stole a lot of his stuff when I did this, and I emailed him and asked him if it was okay. But basically, I wanted to modify it a little bit, just because I wanted to teach it more step by step, and his is more like, bam, here's everything. So, anyway.
Did he respond to your email?
He did. He's a very nice guy. He's very, very gracious to respond. But you can see this worksheet is basically all the stuff I did for examples. It's super long, so I don't expect you to do it all tonight, especially the plotting and the equation converting. But see how much of this you can figure out before I post the answer key. Okay? I will post an answer key, probably Monday night. But this is due Monday. It's just too much to do 37 problems. But now you're thinking sort of in 3D, and equations are more meaningful now. And there's a lot of things that have names too, like some of these things, like if the edges aren't straight on a cone, it's called an ellipsoid, or stuff like that. So we'll talk about a little bit of that. Our main goal is to get back into calculus, but we need some geometry first.